Okay, we're back live. Rise and shine. Time for science. Let's see what we've got here. This is a synthetic test. Hmm. Yeah, this is not very good. Okay, let's figure out why. What's this thing doing? Okay, this one worked. Hang on, this worked. Look at this. This is perfect. Yeah, this is a perfect sweep. We have almost. Gamma's got drift. Yeah, these. I'm surprised it's actually found something with this because there's a lot of drift here. Don't we have cost on here somewhere? We have cost logged. We're just going to do a short morning session today on these experiments. Um, I'm not doing this whole day today. I got stuff to do off stream, but we're going to do a quick morning session on experiments. Maybe I'll do another afternoon session once they're done. We'll see. Okay. This is the test, but when we have sweep carbs, as we don't log the uptime, we should log the uptime. Oh, you know what we can do? Hang on, we can do. What's target metric? Stats a target metric. Uptime. So we'll do cost, cost. We'll do score. Okay. And then can I log this? I like this because this gives me consistent plots for everything regardless of the metric name. So that'll help with that, but then for now, let's take a look at this. Do I believe that this is really cost? Let's do this for now. Okay, this is not terrible. And then the Pareto front, environment, uptime. That's really not bad. The thing is that I suspect that this can be done faster. Why is the data so... It's like so collapsed, right? We definitely have to look at this. This actually might be me having overfit the synthetic task a little bit. This is crazy. I have like multiple accounts following me that I'm pretty darn sure are bots that have thousands of followers. Okay, so like this is pretty decent, right? The score is decent enough. 20 plus is considered solved. So this is very decent. Like it doesn't take very many trials and get good perf. But then the total time steps, it goes down here and it manages to find. So these runs here actually are like 30 million steps, and then it finds 20 million step runs. Let's see the cost. Yeah, you see it takes the cost back down, which is really nice. But I'm suspicious about stuff like this. This seems like it's stuck and it's too conservative. And this is after having doubled all the search ranges. I think I'm penalizing it too much for uncertainty. Let me think about this. Yeah, because this is not what you want this to look like. Really. I mean, it is possible that this is just the optimal, but I don't believe that in so few samples. Like 8 mini batches per Pong? Now that's very slow. Well, hold on. They do have batch size. With a very large batch size, this actually could be good. And that 32, yeah, that's a 32K mini. Okay, so that's actually maybe a decent parameter. Hold on. It's found a pretty high learning rate. Gamma locked to the top has got to be a bug. Pong doesn't have that high of a gamma. And then the lambda up there is also, yeah, okay. So there's some drift. I also don't believe that they can't find a lower update epoch solution. And numEms at 256 is going to slow it down a fair bit as well. Well, I mean, the good news is now we can do these ablations on a real environment. Let's take a look at breakout for comparison. Okay, so this is finding better solutions, but this is running for way too many steps for this core. It's got batch size locked to probably not the best thing. Mini batches is reasonable for the batch size, but it's like not explored this at all. I could believe the learning rate. Gamma is maybe a little low, I could believe it. Same with lambda. Okay, this is, one update epoch, I'm down with that. This is actually not, these parameters don't look terrible. But clearly it's not exploring sufficiently. Well, the cost is actually pretty low here, though. Well, in 1,000, it should be able to solve in about 1,200. And the Pareto fund is pretty messy, but we know breakout is not a breakout has a lot of sample variation. I think what we're gonna do here is let's just say do 300K for breakout normally. This with 4 update epochs. Oh no, there's 1 update epoch, but I think I might have changed this. Let's just put this Pong configuration. Just put this Pong configuration into breakout. This could potentially be a little bit better. This is not going to magically solve everything. We still have some tweaks to make. The only thing we need to change is this is going to be from, I think, 2E8 to 1E9, and with a mean at 2E8. I think that should be good. 200 million steps. Yeah, so this should be fine right here. Two. Okay. So now let's go back to Pong for a second. This solves fast, but I think that the cost isn't there. It is correctly pushing towards lower cost. It's not exploring. This is very few M's to have. A lot of update epochs. And then these parameters seem off. My guess here is that it is oversampling. It's oversampling. Well, it's either oversampling around a single Pareto front, or the trust region around the parameters is too conservative. We have two terms to our loss. Our acquisition function. Why did I make the first term conservative? I made the first term conservative so that you sample. The first term being conservative tells you to make updates evenly along the Pareto front, wherever you are confident that your update will be good. The second term tells you that you should make the highest performing update in which you're confident. So I guess technically you have two confidence terms, so you get confidence squared. Let me try something locally. I'm going to just try this locally, and then I think I'm going to go, I think that's going to just be it. Just a short little morning stream for launching new experiments, and then maybe I'll check back in throughout the day. Because we're kind of in that stage of stuff at the moment, right? Where it's like, we just have to check in on various experiments. My stream offline? Oh no, we're good. Oh hey YouTube folks. This is me checking in on our carbs experiments from last night, hyperparam sweep experiments. We're very, very close to having an amazing hyperparam sweep algorithm for RL. There are just a few small quirks to fix with it. I've mostly redesigned carbs, which is this imbue AI algorithm. I've mostly redesigned it. Actually, maybe I'll go over that out loud because that'll be fun, and maybe I'll catch something that I missed. As soon as I make this one quick change. So the change I want to make is to remove the conservative bound from this. Oh, there's also this exploration bias term that's a little screwy. So we'll have to look at that as well. Okay. So let me go through the changes that I made here. This is carbs. We'll go to paper review mode. This is carbs. View AI released this a year, 2 years ago-ish, and when I saw this, it was a huge deal because they solved ProcGen, which is a pretty good RL benchmark, with the simplest standard algorithm that everyone uses, just tuning hyperparameters. So basically, you don't need to do any of the fancy algorithmic stuff you were doing. All you need to do is tune hyperparameters. Now, this is a pretty complicated algorithm. It involves three different Gaussian processes, a local probabilistic weighting function, and then a clamped acquisition function based on a Pareto frontier, and a few other things as well. So the thing that I did here is I started digging through the code, and I noticed that the way that they were normalizing hyperparameters, they really weren't normalizing the hyperparameters correctly. So it was pretty hard to search over hyperparameter space. It was very unintuitive to configure. So I fixed that, and it looked like it did better. So then I thought, okay, what else might be weird in here? So I started really digging into the math. And the first thing I noticed was this function. What this function does is I should explain a little about how carbs works. So what carbs is going to do is it's going to look at your Pareto points. Pareto points are hyperparameters that obtain the highest score for the amount of time that the training takes to run. So a Pareto point means that you cannot find a better run in the sense that it is going to be both higher score and faster to train. And the set of Pareto points is called the Pareto front. You kind of can draw a curve through that set of points and how much time you have to spend to get a specific score. So what this thing does is it says that when you sample a new point, so you're trying to run a new experiment, you grab a point from the Pareto front, and then you expand around that normally. So you take a normal random sample around this Pareto point. But then what they do on top of this is they downweight points that are far from the Pareto sample. So they have this probabilistic function that prevents you from going too far away from your Pareto points. That seems kind of weird to me because that's kind of just biasing you towards running the same experiments that you already have, and it's doing this in a very unintuitive way. So I just got rid of this thing. And I handle this in a different way. They have three different Gaussian processes that they use. These are learned models that are trained as you run your experiments. They've got GPY, which takes the hyperparameters that you've run, so for all the different experiments you've run, and it predicts the score based on hyperparameters. So it maps hyperparameters to score. There's GPC, which maps hyperparameters to cost, so how long does an experiment take. There are two different models, one to predict how good hyperparameters are, and one to predict how long that they're going to take to run. And finally, there's GPPF, which predicts the optimal performance according to cost. So all that this does is it takes in Pareto points and says how good they are. So this is drawing the Pareto front. This is telling you for a specific cost, how well can you do. Then they have this acquisition function. And what this acquisition function says is if we sample some new hyperparameters, and then we use this, if we use these Gaussian processes, we can estimate what we think that the best you can do for that cost is. So we estimate the cost of the sample, and we estimate what the best that we think we can do is, and then this says how much better do you think you can do than we currently think that the best is. It's a little bit of a weird formulation. I tried replacing this with how good is this point, and it didn't work as well. So this tries to measure the expected improvement over the current expected maximum improvement. These things kind of are fighting a little bit, but it seems like this one works. I got rid of psearch here. They do a few other things though. So there's this major detail where they do acquisition function clamping. And the way that they do this is they try to push you towards higher cost solutions, which really doesn't make any sense. You kind of don't want to go to high cost solutions. You want to go to high performance solutions, regardless of their cost. The way that they do this, anyways, is they replace this estimate with the max of this estimate and a randomly sampled point logarithmically throughout the Pareto frontier. So basically, they can possibly sample a higher cost point that could do better than your current point, and this will increase the max term. So this has the effect of downweighting samples that are low cost. This is a really inelegant way of doing this. So what I did is I replaced this thing, which biases you towards high cost, with a multiplicative term that is just your predicted absolute performance. So you bias towards high absolute scoring solutions, regardless of their cost. I also replaced a bunch of their normalization stuff. They were doing a bunch of like rejection filtering on samples that could occasionally even cause the algorithm to crash. I replaced that stuff with just clipping to within a good search range. And the nice thing about this absolute cost thing that I included is that it's a conservative estimate of absolute performance. So you take your prediction of what absolute performance is, and you're going to subtract the variance of that prediction. So if you're uncertain about a prediction, it gets downweighted. And this kind of does the same thing as this, where here you're downweighting solutions that are far from Pareto points. We're doing something smarter, which is we're downweighting points that you're not confident about the outcome of them. Now, the problem that we're having here is that it's possible for the model to collapse and really only go towards points it's very confident about, which is what seems to be happening here, where it's just not exploring at all around, a specific decent solution once it finds it. So I think that the confidence bound is good, but it's too heavy. You want to be penalized for doing stuff you're not confident in, but you don't want to be so heavily penalized that you only ever explore the exact space of your solution. There's one other thing in here that I don't quite understand, and they actually don't even include in here, which is this exploration bonus. What is this exploration bonus? And is it any good? This epsilon? Did they not say what epsilon is? Explore more. Interesting. So this actually should be exploring quite a lot. because they have an epsilon. They have a pretty heavy epsilon in there. So I must really be clamping this too heavily. Well, I think what we're gonna do, we're gonna go see how this does. And we'll see if this makes a substantial difference. You're not going to be able to tell for a while because you're not going to be able to tell for a little while here though because the first several samples are random. Okay, well, it's Sunday. I've got other stuff to do today. I will probably check back periodically. They're going to be like little random short streams whenever I do experimental analysis here. Because these don't take very long to run. This will be done in like an hour or two. I'm going to probably go get some breakfast, do a couple things, and then check back in. For the couple folks on YouTube, all my stuff's on puffer.ai. The GitHub helps me out a ton. You can join our Discord. There are like 900 people in here building all sorts of awesome RL stuff. And you can follow me on X. There's some custom articles on here as well. RL tutorials, blogs, stuff like that. Thank you, and see you later. Bye.